All right, and then share screen. All right, everybody can see the slide? Excellent. All right, hello everybody. Welcome, as I said, welcome to this first What is Ghost webinar. My name is Zach. I am a science fellow at Gemini North, and I'm also part of the user engagement team along with David Jones and Susan Ridgway. And then joining us today, we also have members of the Gemini Ghost instrument team, Venu Kalari, Jung-Eun Heo, and Emily Diebert. And so the agenda for today is going to be, I'll give a brief overview of what Gemini Observatory is, just as a reminder for those who know, and as a introduction for those who may not really know what Gemini Observatory is and what instrumentation we offer. And then we'll start with the What is Ghost, with Venu giving an overview, and then go into how to apply for Ghost with Jung-Eun, and then finally have a brief demo on how to get your Ghost proposal ready by Emily. So Gemini Observatory, if they will move forward, there we go. Gemini Observatory is consists of two 8.1 meter telescopes, one of which is here in Hawaii on Mauna Kea, and then another in Chile on Cerro Pachón. It is an international collaboration, so the United States is part of this, but so is Canada, Chile, Brazil, Argentina, Korea, and the University of Hawaii. And as we were putting together these webinars, it is great to see that for every single one of these webinars, I think we have every single partner represented as participating in these webinars, which is really great to see. So Gemini has a lot of capabilities in the optical and near infrared. We have a couple of imagers with up to 5.5 arc-minute fields of view, a lot of spectrographs as well, and adaptive optic capabilities. And if you want to learn more about those in details, see our capabilities brochure. These slides will be made available on the Ghost webinar webpage. So you'll be able to come back and look at them if you need, and you can click on the links if you want any references. So to go a little bit more into specifics, Gemini North, as of Northern Summer 2023, has a lot of instrumentation in the optical and near infrared. In particular, for the optical, we have GMOS, which is our workhorse imager, long slit spectrograph, has integral field capabilities, and also has multi-object spectrograph. And this is our most popular instrument here at Gemini North. And then, as I mentioned, there's a Gemini South component, and that is also one of the most popular instruments down at Gemini South. We also have Alapeke up here, which is a speckle and rapid wide field imager. And then we also have high resolution capabilities up at Gemini North with MaroonX, which is a visitor instrument optimized for radio velocities and has a resolution of approximately 80,000, and it's red sensitive. We also have Genius in the infrared, which is a long slit and cross dispersed spectrograph, and recently has new integral field unit capabilities as well. So stay tuned for those. For that later on. It's not going forward. There we go. For Gemini South, we have GMOS South, as I mentioned, workhorse imager and spectrograph, one of the most popular instruments at Gemini South. And then we have Zorro. And in the near infrared, there is Flamingos 2, which is an imager and multi-object spectrograph, GSOI, which is used with GEMS, the multi-object multi-conjugate adaptive optic system, and GEMS itself is being tested for use with Flamingos 2s and GMOS as well. And then in the near infrared as well at Gemini South, you have IGRINS, which has a resolution of about 45,000. Now, one of the differences between Gemini North and South that you may have noticed during this little brief introduction is the lack of high resolution spectroscopy. And that is what these webinars are about, as we are introducing the next stage of Gemini instrumentation with the first facility instrument in over a decade. And to talk a little bit more about them and give you an introduction, I'm turning it over to Venu.
Thanks, Zach, for a really nice overview of Gemini. So as Zach mentioned, we really lack high resolution spectroscopy in Gemini SAT. So can you go to the next slide, Zach? Yeah, thanks. So currently at Gemini SAT, you have GMOS, which I think if you use a quarter arc second slit, you get a resolution of 9,000. That's what you can get because we don't have a NASMET platform in Gemini, so you can't really put big, boxy spectrographs. You don't have a place to put them. Next slide, please. But not for long, because now we have GHOST. And so before I showed you the a spectrum of the O2 lines, and you can see the improvement with GHOST in the standard resolution mode and the high resolution mode. So both of them are respectively at around 50,000 and around 80,000 spectral element resolution. And this is part of Gemini's ongoing program to upgrade its facility instruments. So on the right-hand panel, you can see a graph of our current facility instruments, that wavelength coverage versus resolving power. And you can see GHOST significantly adds to that capability in the optical, and soon you'll have iGrins 2 getting on Sky and Gemini North, which does the same, but in infrared. So GHOST answers this long-standing need for at least the Gemini community of having high-resolution spectroscopy in the optical in the southern hemisphere. And I think what we'll do is there's a vast array of PI-driven science cases that we expect. So in this talk, I'll go through what we expect, and maybe people can give me feedback on what information is needed from us as a science team, but also I'll give an update of the current status and the characteristics as it stands. Next slide, please, Zach. So one of the things, so I just want to show some beautiful spectra in the beginning. So this is XX Ophiuchus. So this is a known iron star. And what GHOST enables is to reveal hidden data, hidden lines and that was not previously visible, at least from the southern hemisphere, to a very broad community, basically most of the American community that didn't have access to the Las Campanas Observatory. So GHOST allowed us for the first time to look at details like, say, multiple P Cygni profiles on this star. And it's not just limited to very faint, bright objects. It's also goes to very faint objects too. So next slide, please, Zach. So this is a quasar around 18th magnitude that was observed as part of the science verification run, and overlaid on the red lines, which is the actual GHOST spectrum, taking around 1 hour, and we achieved a signals noise around 30 at the peak, is a spectra from the DAISY survey, which is also flux calibrated. So you can see the GHOST spectra very closely matches the DAISY spectrum across the broad wavelength range of GHOST. And you can see in a zoom in, you can see the extra features that are revealed by a very high resolution spectrograph such as GHOST. So this is the kind of science cases we expect. Next slide, please, Zach. And I promise this is the last pretty picture we have. So this is TW Hydra at the high resolution mode. So from covering the whole spectral range of GHOST. So from 3,600 all the way to 10,000 Armstrongs. And I think with these spectra, we've demonstrated that this is a new era of high resolution spectroscopy in the optical with GHOST that's now currently available at Gemini South. Next slide, please, Zach. So to give you a brief overview of GHOST. So GHOST is a spectrograph that has on Sky unit and a spectrograph that's connected right at the very bottom to summarize the main science characteristics. You cover the whole optically visible wavelength range in one shot, and you have two resolution choices. You have either a standard resolution mode at around 50,000 and a high resolution mode around 75 to 80,000. I wouldn't really go by the radiovisual precision numbers just yet. I think it's a bit better than that in the standard resolution, but we're still working on getting a long baseline of data to update that number. There's a lot of information about the focal plane and the IFU size. So I think to explain that, it's probably better to explain it with a picture. So next slide, please, Zach. So this is GHOST, and you can see that we don't have a NASMET platform. So the spectrograph is connected via fiber cables. The spectrograph is right at the very bottom of the telescope. You can see the man next to it for scale. And there's a fiber cable running all the way up to the telescope itself, and attached to that is the focal plane unit. So this focal plane unit is zoomed up here, and it's roughly 7.4 arc minutes across. And in its field of view, there's two semicircles, and each one has one eye view each. Next slide, please, Zach. And each eye view is composed of different makeup of micro lenses. And each micro lens, each makeup of the micro lens actually translates to the standard resolution mode or the high resolution mode. So if you look in the zoomed on plot on the right-hand side, there's a standard resolution. So each panel is one eye view. So the left-hand panel is eye view 1 and the right-hand panel is eye view 2. So these two can't overlap, except in the very small overlap region you can see given by the green and the blue lines in the middle panel. So in the left-hand panel, you have the standard resolution eye view on the bottom, the higher resolution eye view on the top, and the standard resolution sky at the, on the bottom left, bottom right, sorry. So you can't change the configuration within each eye view, but each eye view has multiple resolution modes. So in the eye view 2, you have the standard resolution as well, but you also have a high resolution. So in principle, you can have two targets in standard resolution mode and sky as well, but you can't change the position of the sky in principle. And you can also have a high resolution and a high resolution sky at the same time. So that's the different configurations we offer on sky. Now, after the light is fed through the focal plane of the telescope, next slide, please. The light is fed into and received into a pseudo slit. So each micro lens, as you can see, so the numbers on the top panel of the eye view makeup transposed to the pseudo slit, which is also numbered here in two different wavelength ranges. So there's a blue filter and a red filter, and you can see the individual micro lenses from on sky to the pseudo slit. And finally, you can also see it in the spectral image. So can we go to the next slide? So that's the final spectral image. So there's a blue, so the actual spectral image is split again into a blue arm and a red arm, and the dichroic splits at around 530 nanometers. So there's blue detector on the left-hand panel and the red detector on the right-hand panel. And in a zoom up, you can see on one single order, you can see each of the micro lenses. So you can see that from sky to the final image, and this is a flat, but you can also see it on sky images. So it's very good image quality spectrograph. It's a very powerful spectrograph. So next slide, please. So these are the main characteristics that users can be interested in. So this is the throughput on the left-hand panel. So roughly around 10 to 15%, depending on the wavelength range. The slit losses become exponentially higher once you go beyond the eye view size. So each eye view is around 1 arc second in aperture. And if you go beyond that in actual seeing, you start having really significant slit losses. So something around 0.8 arc second, you have minimal, and then you start losing a lot of light beyond that. There's the sensitivity on the right-hand side. So that basically gives you a limiting magnitude of for a signal to noise of 30 in 1 hour. So it's pretty faint. You can get up to 17.6 or 7, depending on your wavelength range of interest, to get good signal to noise to do stellar abundance work and so on. There's on the bottom, I've written the text for the radial velocity precisions. This is analysis that's been ongoing. So we've been taking radial velocity standards for the last few months. We're analyzing them for both resolution modes, and we're seeing what's the fidelity we get in the precision, what's the values we get for the precision. More detailed analysis will be out on the web pages soon, so stay tuned for that. And also our ITC is up to date with the latest throughput curve. So an ITC, which is available on the Gemini website, would give you a very good estimate of the conditions you expect to take your spectra in and what will be the final signal to noise. And that can bleed into how much your radial velocity precision you expect as well. Next slide, please. So in the beginning, I showed an example of different science drivers, and we expect a large fraction of science to be PI driven. So we expect the classical Gemini way of individual programs asking for time and looking at very unique objects, like we showed, like XX of Eucus, TW Hydra, some very well-known targets that new features have been looked at, but also very faint targets like the quasar we showed, but also possibly rapid transient objects. And GHOST, because of its aperture, as I described before, it's around 1 arcsecond for the IFU. It's quite large for the resolution it's delivered because the image is sliced. So you can use it in a wide range of conditions. So and even for bright objects. So we haven't put the figures out there, but we've taken rapidly varying objects with very short orbital periods, and then you avoid phase smearing by taking ghost spectra, even in poor conditions, because you get really good signal to noise over a very short exposure time. Next slide, please. So this is the current status and looking ahead. So we expect a call for proposals with the shared risks. So there's some leeway involved in taking the data or the quality of the data probably, but we expect the data to be of good quality. This call for proposals will come out at the end of this month, end of next month, sorry, along with the regular 23B call for proposals. And then we also expect the 24A it to be included as part of the regular facility instruments in the 24A call for proposals. Now, one of the modes of GHOST has not been commissioned yet, and that's the one with the internal lamp. So GHOST also has an internal lamp that takes simultaneous spectra along with the science on Sky. That mode hasn't been commissioned yet, and so that mode will not be offered until it's fully finished commissioning. Yeah. Thanks, Zach.
All right. Thank you, Venu. And so up next, we're going to have Jung-un talking more about how to apply for ghost time.
Yeah. Thank you, Venu, for detailed explanation on ghost. Hello, everyone. I'm Jung-un from Gemini South, and now I'm gonna cover the way how to apply for ghost time. Next slide, please. Before explaining that, I briefly introduce the system verification. To make GHOST available to the community, we conduct the system verification run in May. During this SV run, we use a total of 40 hours engineering time to test software documentation and all operational procedures. We observed 7 programs covering various science areas, and now you can access all raw data through the archive and more detailed information about the instrument setup and the science case of dataset can be found in the GHOST SV website. And the SV team has some interesting science results to share. So we have a plan to present them in the upcoming webinar, which are scheduled for August 2nd and 8th. So please join in there as well, and let's see exciting findings. So next slide, please, Jack. So now let's discuss how you can apply for ghost time. There are multiple ways to apply. The first open call for proposal will offered in a shared risk mode. So the observation will be executed in November, December, and January, but although the specific date are yet to be determined. The health of the regular fast turnaround time is reserved for this core, so the available time to each partner community is shown in the table. And just like the fast turnaround program, this shared risk call will be in a peer review process. The important thing is the deadline for this call is for submission is September 30. And you have another option to apply. As we expect, the Ghost will be integrated into the Gemini South facility instrument in 24A. You can also apply the standard semester course in 24A, which covers February to July. So please note that both shared list and the standard semester deadlines are September 30, around 2 months left from now. And additionally, we will also offer Ghost for fast turnaround in 24A. Yeah, similar to other instruments, but the scheduling will depend on the instrument availability. So so please stay tuned. And that's a brief overview of how to apply for Ghost time. More detailed information and any update will be announced on the Gemini website. We'll be waiting for your proposals for exciting Ghost observations. Thank you. And I can see some chat. The questions. Yes, that's right. The unit is hour in this table. Thank you, David.
All right, thank you, Jung-un. Moving on, we're gonna have Emily give a short demonstration on how to set up your Ghost proposal. So I'm going to stop sharing and Emily will share her screen.
Yeah, thank you, Zach. So I'm going to go through 3 different tools that will be useful for preparing your proposals. If you're already a Gemini user, then a lot of this will be a bit familiar, but there's just some new added capabilities for Ghost. So the first one I'm going to start with, which is the first thing you'll need to start with when you're preparing your proposal, is the exposure time estimation. We have a tool for this. It's a web applet available on our website. So if you go to the main Gemini website, you go to instrumentation, and then go to Ghost, that's where you'll find it. It'll be on the left-hand side here, their exposure time estimation. And this looks very familiar to the other exposure time calculators for facility instruments at Gemini, but I'll still go through everything just in case you haven't used Gemini before. So the top section here is just, or these first 2 sections, I guess, are for defining the source you're looking at. So there's a lot of different options. I've already plugged a few things in here. The first is if you're looking at a point source, you can plug in the magnitude of your source here. There's other options too if you're looking at something a little more complicated, maybe some kind of extended source. And there's lots of options here for defining the magnitude of your source, defining what band it is that you're referring to. So this will be familiar if you've used Gemini instruments before. This is essentially the exact same as what we have for other instruments. Same down here, you can just choose what kind of object it is you're looking at. So I've selected just a star here, but we also have library spectra for a lot of different objects that you might want to look at. If you're looking at single emission lines or anything like this. So like I said, this is familiar to Gemini users, and there's more info that you can read about it for all these sections if you need more information. The main part I want to focus on is what's new for Ghost. So this is this section here. There's not too much compared to some of our other instruments, so that's nice. And this should be familiar from what Venu just explained about the instrument. The main kind of decision you have to make, I guess, is whether you want to use the standard resolution mode or high resolution. You'll recall, as Venu said, that standard resolution is about 50,000, high resolution is about 75 to 80,000. The only difference that will change in this section here, if you click high resolution, is you no longer have this choice about the sky micro lenses. So you can see it says here only for SR mode. But what does this mean, the section about those micro lenses? So if I have standard resolution chosen, if you recall from the image that Venu showed earlier, the default in standard resolution mode is to have your object that you're looking at, and there's a sky micro lens with 3 fibers that you cannot change the position of. But as you recall, standard resolution mode has this option to observe dual targets. So you could be observing, say, 2 stars at once. But if you want to use that other IFU to look at the sky, adding additional sky fibers, you can also do that, which is when you would choose 10. That's you have the 3 default and then the extra 10 from another IFU. 7 would be the case where for some reason you cannot use those 3 that are normally on the sky. Maybe they're on an object because of the way that you've set things up. And then you would just have the IFU2 on the sky. But the default is usually 3 if you're not using that extra IFU on the sky. There's various binning options here, spectral and spatial. So it's kind of up to you for your science if you want to bin. And there's also various read modes. All of these options here, I would recommend to read on our website about the capabilities because that'll describe more under what cases you might want to change the read mode. For example, if you have a very bright object you're looking at, you might want a fast read mode. But I'll leave these both in the default as well. This section here, you don't have to worry about because that is, it just talks about how the instrument is positioned on the telescope, and that's not something you can change. The next 2 sections are also familiar if you've already used GHOST before. This is just to choose the constraints for your observing conditions. I won't go through what all of these mean, but if you have questions, you can definitely ask us at the end, or you can read on these links here. So this should be familiar if you have used Gemini before. And then finally is just choosing the exposure time you want. So I've plugged some things in here. I just did a simple example where we take 1 exposure with an exposure time of 140 seconds. If you calculate, that will then open a page in a new window which has your results. So again, this is familiar if you've used Gemini before, it's the same kind of layout. Up at the top, it just gives you some information about, for example, if we had overexposed here, it would give us a warning up here. Some details about the overheads, so the time associated with acquiring the target, time associated with reading out and writing out. So these are things you can play around with. If you think maybe you want a faster readout time, then that was an option back in the page we were on before. And then down here, we have the actual results. So it shows kind of intermediate steps, but the very final graph at the bottom shows you the signal to noise of your final spectrum that you have. So as you can see in this example I chose, it's quite high, it's 600 or so. But yeah, that's kind of how you use the exposure time calculator. One thing to mention, which I think will be more clear when I show you the observing tool, is you can choose different exposure times for the blue and red cameras. That isn't something you can plug into this exposure time calculator, whoops, that we have right now. So you might want to do a couple calculations if you're thinking of doing a different exposure time in the blue and in the red. So that's kind of everything for the exposure time calculator. I know there's some questions in the chat maybe, so I don't know if there's anything that anyone wants to ask right now, or if not, I can move on to the next tool.
Someone was just asking about the sensitivity, the magnitude limits.
Okay, maybe we can answer that at the end, unless they were wondering specifically about what we can fit in here. But I think maybe we can save that for the end. So next, if there wasn't anything else about the calculator, I will go to the phase 1 tool. This is also familiar if you've submitted proposals to Gemini before. It's the same tool that we always use. When that call for proposals comes out that Gemini was mentioning, there will be a phase 1 tool for you to download for the next semester. So I'll focus here on the actual things that you input. I've already input some details here. If you haven't used this phase 1 tool at all before at Gemini, we do have resources available on the website to kind of walk you through it. But what you really need to know is that there's kind of 4 different sections you have to fill out here. So the first is the observing conditions. I just kind of mentioned that in the exposure time calculator as well. This is just to decide what conditions you need for your program. This section here is kind of the main section that has to do with GHOST. So as you can see here, GHOST is now added to our list of instruments. As I mentioned before, there's these 2 different modes. And if you select either one of these, you're going to get different options. So you'll see I've selected standard. I have 3 options here. These are what I was describing before. You can observe a single object in standard resolution mode. You can observe 2 objects in standard resolution mode, or you could observe an object and then have that second eye view on the sky. Those are the 3 options for standard resolution. If I were to choose high, there's only one option. You can just have single and you always have a sky fiber. So we'll go back. And then similar to our other instruments, you just input your target here. You can look it up or you can put in the coordinates. This is familiar from our other instruments that we have at Gemini. And then finally, you can input your observation time. If there were night baseline calibrations that were associated, they would automatically calculate here. But maybe we can talk a bit more at the end about what the calibrations that come with ghost data are. They're also outlined on our website. But what you just have to worry about here is inputting the amount of time you need for your program. So that's essentially it for the phase 1 tool. It's pretty straightforward, especially if you've used the phase 1 tool before at Gemini. There are also sections over here to actually input your proposal, but that's not ghost specific, so I won't go into too much detail unless anyone has questions about that at the end. But if there are no questions specific to this in the chat, then I will go to the observing tool because that's kind of the bulk of what people might be interested in. Okay. So lastly is the observing tool. This is what you use to actually set up your observations once you've been allocated time with Ghost. Again, if you've used Gemini before, this will be familiar, but there's a lot of updates for Ghost. So I'm going to walk through. I have 3 different examples set up here for this kind of 3 main modes I mentioned, which are standard resolution with a single target, standard resolution with 2 targets, and then high resolution mode. So again, if you've never used the observing tool at Gemini before, it might look a little overwhelming, but we have resources on the website to kind of deal with how to use this. So I'll just kind of go over the sections that are specific to Ghost that are new for Ghost, which is the Ghost component here. I'll just go through from the top to the bottom, everything on here. For the most part with Ghost, you don't have to adjust the position angle, so you don't have to worry about this first part too much. What is going to matter most for your program is choosing your resolution mode, your target mode, and then all the details about your actual observations. So like I said before, there's these few different resolution modes. You'll see that the precision radial velocity mode is listed here, but it's not going to be available yet. So I'll skip that one. It's still commissioning, as Vinay mentioned. But starting with standard resolution mode, there are a few different options for your target mode. Like I mentioned, you can observe a single target and observe 2 different targets at the same time. You can have IFU1 on your target, IFU2 on sky, and then the reverse if you wanted that. Something unique to Ghost, like I mentioned, is that you can have different exposure times and different numbers of exposures in the red camera and the blue camera. So I've set this particular example up like that. In the red, I'm saying we have 140 seconds for exposure. In the blue, we have 300 seconds for exposure. Something a little different about Ghost compared to other Gemini instruments as well is that you have the option in this page here to change the numbers of exposures that you have. So in this particular example, we have red exposing twice for 140 seconds each exposure, and blue observing just once for 300 seconds for that exposure. So again, this is a case where you might want to do a few different calculations using the exposure time calculator to figure out what's going to work best for your sources that you're looking at. You can also adjust the read modes. They're right now just set on the kind of default, but if you had a target that was really bright, for example, you might want to adjust those. And then again, you can adjust the spectral and spatial binnings with the same options that you saw on the exposure time calculator here. Down at the very bottom, this is also details you don't necessarily need to worry about because it relates to how the instrument is actually positioned on the telescope, and you can't change that. The other kind of main component to look at for Ghost is the target component here, which again is similar to our other Gemini instruments, but there's a few details specific to Ghost. Something that'll be useful for you. So right now I've input a target in here. you can click on this image component up here to actually look at what your target is. So we're just looking at a star here, and our auto guide star tool has picked a guide star for us. So in this mode where we have just a single standard resolution object, it's fairly straightforward. We just see that object here. The next example I'm going to show is the dual target, which is a little more complicated when you look at the target page. So just briefly, I'll go to the ghost component again, and you can see I've now selected dual target here. Aside from that, everything is the same as the previous observation I was looking at. But now when we go to the target component here, you can see that there are two targets for IFU1 and IFU2. What's important to do here is make sure that you've typed in your components properly or looked up your objects properly, so that they're both, it's the correct objects you're looking at, and they're both going to show up in that field of view when you click on the image. You can see here now I have these two IFUs with two different stars selected. IFU1 is here, IFU2 is here. And they're kind of, the base of the instrument is kind of equidistant from these two objects. The way to make sure that happens is you start with the base not linked to target. You'll input your two targets, your two stars, and then you hit link base to target, and the system's going to automatically kind of do that for you. Make sure the base is equidistant between those two targets that you have. So that's the standard resolution dual target. The last mode that we'll have available right now is the high resolution. When I select high resolution in the resolution mode, it's fairly straightforward because there's only one option here, IFU1 on the target, and then you also have this dedicated sky fiber. So now if I go to the target component here, you'll see that's a slight difference. It says IFU and then sky as well. If I go to the image, you can see those both here. The source is now centered because we just have one source, the IFU is there. And then we have this right here, the sky. Something to note, so I've set up the sky in kind of a location here, but if I decide actually I don't think this is a good spot, I think maybe there's a star where I've put the sky, so I'm going to move the sky fiber. The way to do that, or one way to do that, if you don't know the exact coordinates of where you want to put it, is to go over here on the left-hand side and click user, and then you can drop a pin kind of where you want it. So let's say I've decided this is a really good spot for the sky. I'm going to drop that pin there. And then when I go back to the target page, I now have these coordinates that I've dropped. I can copy those and then paste them in here to the sky. And when I reopen it, you can see that now the sky has moved over here. You could also type the coordinates manually if you happen to know exactly where you want to put your sky. But I think in most cases, you might not know that. And so you might want to look at the image and choose where you're going to put it. So that's kind of the main details you need to know for high resolution mode. The other mode, I guess, to know is that, as you saw in standard resolution, you can also just choose to have IFU2 as a sky, and then that will be similar to what we've chosen or what we did before with the high resolution mode. It's just that now one of these IFUs is on the sky rather than on an object, and you would as well select where you want to put that. So those are kind of the main modes, but I'm sure people have questions about specific setups or things like that. So maybe I'll stop sharing for now and just take a look at the chat, or if anyone wants to read out any questions.
Yeah, I can read a couple questions. I think they're getting answered in the chat, but the first question is, what are the separation restrictions for observing dual targets?
Yeah, I see, David, that you answered in the chat, so that's great. I believe that's correct. So 7.3 arc minutes. You on the tool, the observing tool I have here, if you were to put, maybe I can share again and demonstrate this. If I were to have chosen two objects that it's clearly not going to work, they're too close together. Let me do this quickly. Oops. Well, the point is, if I do something very wrong, it's going to tell me over here. I think I've already accidentally done that. Yeah, so you can see here, it says the coordinates are out of range, or it's going to say they're too close. So the tool will warn you if you're doing something wrong. But yeah, it's good to keep in mind there are limits.
And I believe there was 102 arcsecond minimum separation. Thanks, Zach. The second question was, what are the readout times for the various modes? And Jung-Un posted a table.
Yeah, in the Ghost component webpage, we put the table indicating all readout overhead for each mode, each different mode. So you can find. Well, I could share. Yes, here. So you can find on the webpage.
And the next question was, dual targets must be separated by at least 102 arcseconds. This restriction leaves out many visual binary systems. Is it possible to decrease the minimum separation?
Yeah, hi David, I'll take that one. I don't think you can do that. It's a physical collision between the two IFUs, so that'll break the whole instrument. So no.
So twice the exposure time is needed for those. The next question. Sorry, I think I lost track of things a little bit. I think there was a question. Maybe Ting. Oh, in the proposal, can we specify the sky location, or is that something determined by the observer in Q mode observation? And I think from your demo, Emily, the observer can specify it in the observing tool before it goes to the Q operators.
Yeah, in the proposal, it wouldn't be necessary to, I believe it wouldn't be necessary to write the exact location while you're proposing. You would just choose that when you're setting up your phase 2.
And then there was a question about cosmic rays. With GMOS, there's a maximum recommended exposure time of 20 minutes because cosmic rays. Do you have a feel for what this would be for Ghost?
Hi, David. Yeah, I'll take that one. So thanks for your question, Steph. You can go up to 1 hour and the data reduction deals pretty okay with the cosmic rays because it's in a shell. You don't get, it's not that much of an issue as with GMOS. So I would say 1 hour. You could probably, if your target's super faint and you can deal with it yourself, you could probably go to 4,500 seconds. But I would say 1 hour would be the maximum, a single exposure. We've done that and we've got decent data.
Great, and I think that was everything from the chat.
Yeah, so thanks again, Emily, for that demo. I'm gonna share, well, let's see if I'm able to share screen again. There we go. So just to kind of, well, let's go back a slide. Just kind of wrap up for everybody. So here are some of the resources that are available for your proposal. Again, we're going to make these slides available on the Ghost webinar webpage, and these are all also on that same page. So it should be convenient to go grab them. And finally, we're just going to open this up for Q&A. There were a couple questions that were brought up on when you filled out the webinar form. Here are a couple of them. I think Venu covered the stellar velocity precisions and repeatability for Ghost. Unless you want to add more, Venu.
No, I think that's a work in progress. So I hope to update the web pages with the RV precisions we can get probably around the time of call proposals. So in around a month.
Okay. There's another question. Yeah, so this will kind of, I think this will tie, this can tie into kind of the last point on this on the slide about telluric corrections, Ben is asking what are the wavelength and flat fielding processes. So what are all the calibrations that will go into ghost data?
So as part of the, so Gemini has two types of calibrations, and they're all described in the web pages. The first set is the baseline calibration. So that's taken as a legacy for all our service instrument or our facility instruments. So these include a flat, an arc, and biases for whatever mode of the data that's been taken. And a standard star sometime around, maybe not that particular night, but a few nights later or before, whenever the conditions suit. Those are our legacy calibrations that are taken regardless. Now, other calibrations, for example, the telluric standard or an RV standard, these have to be part of your science program and have to be included in the time you ask for the proposal. And then you can use that telluric standard star to subtract your telluric, or use the RV standard star to, use your RV to whatever you want to do. I see another question. The baselines are done during the day. I think the instrument is very stable enough that there's no real difference. You don't need to do an arc during the night. There's no flexure. The instrument is a box in the peer lab, in the bottom of the telescope. So there's very little flexure.
All right, and then we had another question in chat about the kind of sky conditions that are going to be available during the shared risk call. And I believe that you're correct that they will break down following the normal fast turnaround procedure. IQ 20 can be requested up to 20%, but just to confirm, I'm going to look to everybody on the ghost team.
Yeah, I think it's the same, Zach. So there's different quartile bins and how much you can ask for IQ. We've requested to include some time for SB20. So that's when your really faint targets can be observed, sometime for SB20 and SB50. And everything else, the conditions itself, I don't know, it's a guess, right? What you get on sky at that particular some point in time.
All right, I just saw one of the questions. So for who evaluates the shared risk, you guys are. It's going to follow the same process as FT, where if you submit a proposal, you will be given a set of other proposals to grade. So, so we have a question for the ITC. In the case of giving different exposures for the blue and the red, how can we apply it to the ITC? Should we set the spectral range manually?
Yeah, so the way it's set up right now, that would be the best way, I think, is to just do different calculations. If you think you need a different exposure time in the blue and red, you could do those separately. You have the option to just look at set a spectral range similar to our other instruments, or you could output the whole thing and see the whole spectrum. But yeah, as of right now, there isn't a way to input both those two different exposure times.
All right, and then I saw something else. Okay, so the last item on this on the slide, is there any? So the high resolution mode is only a single fiber, but in the case of using standard resolution mode, is there any difference between observing single target and two targets in terms of resolving power?
No, it goes to the same spectrograph. So there's no difference in the resolving power, but there is difference in, so if you use IFU1, you get the sky always in standard resolution, but if you use IFU2, you can never get the sky. So we offer for standard resolution only IFU1. If you're using only one target, only IFU1 you can use. There's no difference in resolving power, and there's almost no noticeable difference in throughput between the two IFUs for standard resolution.
All right. So before I go on to this question, I'm just going to move it to the next slide and open up for general questions, which we have been doing, but just to move it to that slide. So Guy is asking, can you do two exposures with either camera when the exposure times differ? For example, 400 seconds in the blue, and then 2 exposures of 180 seconds in the red.
Yes, you can. Sorry, I didn't know if someone else wanted to take that question, but yes, exactly. You can set different exposure times for those.
All right, are there any other questions that people have? Okay, Jose is asking, what is the typical overhead?
Yeah, I can take this. So the overheads, it'll tell you when you use the exposure time calculator, what the estimated overheads are. They're not too large. Right now, we've said 15 minutes for the acquisition. And then depending on the readout mode that you've chosen, that's going to differ slightly. So if you look at the table that Gemini links, that'll tell you the overheads associated with the readout and the write out. But yeah, it'll, once you input everything into the exposure time calculator, it'll tell you those numbers for the readout mode that you've chosen.
All right, if there are no other questions, then I'm going to say, oop. Ben is asking, how does acquisition work?
This is a very good question. So if you can go back on the slide, Zach, to the slides where the 2 IFUs are visible. Yeah. So if you see in that, Ben, you can see around the science IFU. So the science IFUs are marked in blue, and around them there's like a red micro lens. Sorry, each hexagon is a micro lens, and around the science micro lenses there's a red micro lens, and that's a guide micro lens, and that is used to center the object. So once the telescope's loose roughly to where the target is, those micro lenses get the light, and the centroid is calculated for where the star is, and that centers the target, the star, in the middle of the IFUs.
All right, we're approaching the hour, so I'm gonna say if there are any more questions for Ghost, please don't hesitate to email the Ghost team, which is at ghost_science@noirlab.edu. And I want to thank the members of the Ghost instrument team who gave their presentations today, and I want to thank you all for coming and listening as we bring in this new era of high resolution spectroscopy at Gemini South. And hope to see all your proposals in a couple months. So thanks for coming.